Thank you for that introduction. I'd also like to thank the organisers for giving me the opportunity to speak today. I've gone a slide on. Okay. So today I'm going to talk to you about SIMBAD. I'm going to talk to you about that in the context of contaminants and also sequence-independent molecular placement. So I thought I would first just give you a little bit of background about the sort of conventional way we do things. And so we just normally will take the sequence of the protein, we'll identify some suitable homologs, we'll chuck them into our MR program, and for most cases this will work wonderfully. However, when it doesn't work, it can be incredibly difficult to solve these cases. So what is SIMBAD? Well, SIMBAD is a sequence-independent molecular placement pipeline based on available database. What this does is it exploits features of your experimental data directly to try and identify suitable search models. So Eleanor said earlier in her talk that identifying a search model is the most important thing in molecular placement. We're trying to do this without sequence. So the scenarios where SIMBAD might be able to help. If a contaminant crystal has been protein has been crystallized, that is very, very hard to solve because you'll be just led up the garden path trying to solve it with the wrong sequence and you won't be able to find anything. Additionally, if you don't know the sequence of your protein, you can't use it. Occasionally, you might have a high percentage sequence identity homolog that undergoes large conformational changes. I think we've already talked about some clever ways you can do this when you know the sequence, but it's just the idea that you might have a hinge protein or something and it is difficult to find. And finally, the homolog just might not be obvious from sequence alone. So how does SIMBAD work? Well, molecular placement is split up into two steps. The first one is rotation search and the second one is translation search. It's sort of a given, if molecular placement is to work, the rotation search has got to work. If the rotation search gives us enough information, we don't actually need to do the translation search for it to give us, is our search model likely to work or not? So I've drawn out some simple Patterson maps here. Eleanor talked in great detail earlier about the Patterson maps, so I'm quite thankful for. But on the left-hand side here, you've got some very, very simple 2D experimental Patterson maps. And on the right-hand side, I've got a good Patterson map and a bad search model Patterson map. I want to just show you here that if we sort of rotate these on top of each other, you get here a overlap score against your orientation. Now, when we have a really, really nice search model, we're going to get large peaks at certain orientations. Whereas if we have a rubbish search model, we're just going to get a noisy sort of result out. In normal molecular placement, you're just going to use these peaks to say, okay, we think the orientation is here. But we're not really interested in that in SIMBAD. We just want to look at this distribution and see, can this tell us something about our search model? And if we take a z-score of this, you'll see that at the top we get a very large z-score, or higher z-score, and at the bottom we have a much lower one. All we're really doing in SIMBAD is we're running a rotation search against every structure in a database. We're ranking them by z-score, and the search models that are going to work better in molecular replacement are going to have a much higher z-score. The next consideration we needed to make here was what database do we use? The one we decided on was the MoRDa database. MoRDa has got the advantage of being a lot less redundant than the PDB in full. So this means if you consider in the PDB, there are a lot of examples where you have a protein that the only thing that's changing is it's got a new ligand attached to it. We don't want to run all of these as it would take a while. So we use the MoRDa database as it's much, much quicker. And additionally, it's made up of domains. This gives us an advantage of being able to solve novel structures. If you imagine the Lego analogy for domains, you can sort of see that you might have a known domain in a novel structure, and this known domain might allow you to sort of bootstrap to the novel structure. So I'm going to go through now some examples of where SIMBAD has been able to work. In this first example, the target protein was expressed in E. coli cells. After several months, the crystals grew, and the homologs that they found just wouldn't work. We chucked this into SIMBAD, and it readily identified that it was a contaminant. Another example here, target protein, crystallized, I think, expressed in insect cell line this time. Crystals obtained after a few months. Homologs failed. Yeah, it was contaminant again. This case, this one's a little bit more interesting. So the target protein was expressed in the E. coli cell lines. This time they did a mass spectrometry on their protein, identified that, yes, we have purified the correct protein. Tried with homologs. Yeah, it was contaminant. Of course it was contaminant. I was going to leave this here, but I thought it was too good not to sort of mention this. Even a lot of you will have already seen this at the MR clinic. They were taking we took a load of sort of cases that were very hard to solve. It's a very familiar case. I'm stamping it. It was a contaminant. So it happens very frequently. It's the #1 scenario where SIMBAD works. And this has led Ronan to redub it Simpkin's bad news server, as opposed to, yeah. I think people are very rarely happy when I tell them you've got a contaminant. I've seen the full 5 stages of grief, you know. It's worth mentioning now, though, we have been able to solve some novel structures. There was a group in Brazil who had a snake venom that they hadn't sequenced. We were able to solve that one. I was very pleased as they were actually happy for once. So that was quite nice. So I did mention the MoRDa database earlier, and it is actually quite a large database. Seeing as we were getting so many contaminants, we noticed that most of them were the same contaminants over and over again. So we compiled a list of contaminants from Marston at CCP4 and global phasing, and also from the Contabase from Contaminer. And using the exact same rotation method I've already mentioned, we're able to much, much faster sort of identify a contaminant. Additionally, if you have a protein that's already been crystallized before, there's a good chance that it's going to crystallize in exactly the same form again. So we just do a lattice search. We look at the lattice parameters for our experimental data. We compare them to the lattice parameters in the PDB. And if we have anything that's similar, this is, I think as Eleanor said earlier, just a refinement problem, and it can be really, really quick to solve. So I want to show you the full pipeline as we've created it so far. We take your experimental data. We put it into the lattice parameter search. If we find something, wonderful, let's stop there. Otherwise, we'll try a contaminant search. Again, find anything? Wonderful, done. Finally, if we don't find anything with those 2 methods, we can be more confident that the MoRDa search might actually find something that's new, interesting. So I wanted to talk about how we tested SIMBAD. Before you have 25 proteins that were newly deposited to the PDB at the time and therefore hadn't made their way into the MoRDa database. When we ran this through with a MoRDa, we managed to solve approximately half of them. We then looked at our data with a little bit more interest, and we noticed that about 6 of them had nothing similar in our database at all and would never have solved. So for the purpose of what I'm going to talk about next, I think we can just ignore them. And finally, we had this little group here, which they definitely had structures that would have solved them by molecular replacement, but for whatever reason, we weren't able to identify the search models. So I'm dubbing that room for improvement. So how are we planning to improve SIMBAD? I say planning. How are we improving SIMBAD? So the current method that we're using with a MoRDa has got some pros and some cons. The pros are it's really fast, and most of the time it works really well. The con is that it doesn't really account for any error in the model. Phaser, meanwhile, uses a maximum likelihood method, and therefore the maximum likelihood calculation can sort of account for errors in your model. It also, as Ellie talked about earlier, can use ensembles, which are really, really useful. The one con I have, though, is that I was really excited about using Phaser and being able to put the error into it, but then I realized that I actually had to estimate that error in some way. This is actually more difficult than I was expecting it to be. So accurately predicting model error is really, really important, as it turns out, in the more tricky cases. Traditionally, this is done, as it seems everything in Phaser is traditionally done, with sequence. Sorry, did I say Phaser? I meant molecular replacement. So we look at the model, we look at the sequence from the model, we look at the target, and we sort of compare the difference, and looking at the difference between the two, we sort of work out what we think the model error is going to be. Oops. But if we don't know what the target is going to be, as is the case in SIMBAD, we can't really do this. So currently, we're just doing a sort of educated guess that we think will work well most of the time. As clarified, this is a work in progress, so hopefully we can improve this in due course. The other great advantage of Phaser is that you can use ensembles. So an ensemble generates a statistically weighted average model. What this means really is that it downweights the really variable regions of the protein and works better than a single model. I've already had some success with this. So you can see here I have a target on the left, and it looks really, really similar to the single search model. But when I put this through the rotation search, the single model was unable to give me the sort of scores that I would go, wow, this is a good search model. Meanwhile, just changing it so that it's an ensemble like this, that suddenly gave really, really high scores, and it was able to come out #1 in the search and solve really quickly. So SIMBAD is available through the command line, CCP4i, CCP4i2 now, and much more recently it's been made available through CCP4 Online. I'll put a caveat here with CCP4 Online. Currently it's just doing the Lattice search and the contaminant search. It's not doing the MoRDa search yet, but hopefully we're going to get that done in the new year, or not new year, later this year. Additionally, you heard about CCP4 Cloud earlier, and it will be available when that comes later this year. Dan talked about citation tabs. This will look very familiar because I stole all of Jens's code to do it, and I put it directly into SIMBAD, so we're doing exactly the same thing here. And I just wanted to give you some very brief conclusions. So the SIMBAD lattice and contaminant search can be run really, really quickly, and they can be used as a sort of first step to just make sure that you don't have a contaminant. Currently, I'm sort of implementing this at Proxima 2, where I worked for 2 years, as part of their automated post-processing step. That way, you'll be able to identify your contaminants first step quickly. It also is going into CCP4 Go, which is the automated CCP4 Cloud utility. I think I should also mention at this point, if any of you have got MR problems that you've been trying really, really hard to solve for ages, you should probably just chuck them into SIMBAD and double check. For more difficult cases, I don't think that you should be scared of trying to run the full SIMBAD search either. It's a much bigger search, but it is tractable. You can do it on a cluster quite quickly, less than a day. I've also run this on my desktop at home in, I think, 2 to 3 days. So it's not ridiculous. Finally, I'd just like to give out some acknowledgements. So I'd like to acknowledge Dan and Ronan, who are my supervisory team at Liverpool, for all the sort of help and advice they've given. Charles implemented the Z-scoring function into MoRDa. Vili helped me put SIMBAD into CCP4 Online. Likewise, Eugene helped me do it into CCP4 Cloud. Andre and Alexei gave me lots of advice about putting it in using the MoRDa database. Martin helped with the contaminants. Bill and Martin were my supervisory team when I was stationed in Soleil. Felix, who, again, Dan said is sadly gone, he put a lot of code into this as well before he left. Jens also has added some code too. Randy gave me some advice on Phaser, and I'd like to thank Maria, Ray, and Yibin. Actually, I also thank Cameron here, I didn't put his name here, for giving me contaminant cases to present to you all. Thank you. If you have any questions.
Thank you.